Hello everyone, welcome to this video. In this video, we shall be solving this question which states that we need to prove the set of all 3 cross 3 matrices with real entries of this form, where we have on the diagonal all the elements as 1. The lower side of diagonal is all 0 and the upper side contains the numbers A, B, C, where all the entries are real numbers, correct? So we need to prove that this forms a group. And what is the group operation that is given to us? We are given the group operation as multiplication, where it is defined in this manner. That means it is the usual matrix multiplication. You have the first element as when you multiply this row with this column, right? And you have the second element as when you multiply this row with this column, correct? So 1 into A dash is A dash, plus A into 1 is A, plus B into 0 is 0, right? In this manner you can calculate all the elements. This is given to us. Now we have a note here suggesting that this group is sometimes called the Heisenberg group, right? It is named after the Nobel Prize winner physicist Werner Heisenberg, and you might be knowing about this physicist really well because he is related to this uncertainty principle, Heisenberg's uncertainty principle, which was named after him, and this principle is found in quantum physics, right? This thing is there about this group. This is known as Heisenberg's group, correct? Now let's move forward and prove that this is a group. Now in order to prove that it is a group, we need to prove 4 properties. First one is the closure property, second one is the associative property, right? Third one is the existence of identity, where you need to find some element within that set such that it act as identity, and then we have to check that whether each element here would possess an inverse or not. If all the 4 properties are there, then we say it is a group. So moving forward, first of all, let's see about our closure property. For that, we take one element 3 cross 3 matrix of this kind, another 3 cross 3 matrix of this kind, and you multiply them. So you see here also we have on the diagonal all the ones, here we have all the zeros, and here also we have some non-zero members, correct? So therefore it is again of this form with real entries, hence we say the closure property is satisfied, right? All the entries, they are real in nature. And this for the second property, as matrix multiplication is associative, you know that, hence we have the associative property valid here in this particular case, correct? So we also have the second property with us. What about the third property, the identity, the existence of identity? So here we have some matrix which we are calling by I, right? So this matrix contains all the elements at the diagonal as 1 and all the other elements as 0. Now we say this forms the identity of this particular set. Why? Because all the entries, they are real in nature, and it is a 3 cross 3 matrix, so it is taken from this set of all 3 cross 3 matrices with real entries, and it is of this form, correct? So this forms the identity here. Why? Because if you multiply it with any matrix, you will get back that same matrix, right? So we have the third property valid here also. For the last property, to check the existence of inverse, let's take any arbitrary member, say capital A, from it in this form. Now we wanted to check whether it possesses A inverse. If yes, what is that inverse? So we are looking for such an A inverse such that when you multiply A with A inverse or A inverse with A, you will get back the identity element, which is the identity matrix. So you might be knowing the formula to calculate this inverse of 3 cross 3 matrix. So here, to find the inverse of a 3 cross 3 matrix, let's take first of all calculate what is the determinant of this matrix. If it is non-zero, then only we can proceed. So if you can calculate it, and you can see here the determinant comes out to be 1, which is non-zero, hence we can proceed towards calculating its inverse. Now in order to calculate the inverse, if you remember, the inverse of matrix A is 1 by the determinant of this matrix, and then we have to multiply by the adjoint of this matrix A, right, which is again a 3 cross 3 matrix. So let's first of all compute what is this adjoint A. So in order to calculate adjoint A, if you remember what is adjoint A, it is the transpose of cofactor matrix. transpose of cofactor matrix. So first of all, we'll be calculating what is our cofactor matrix here in this particular case. So you see, first of all, for the cofactor matrix, you have to calculate all the minors and then substitute the values here, right? We can directly do that. You know, this position is A11, this is A12, this is A13, this is A14, A15, according to row and column, this should be second row and first column. This is second row and second column. This is second row and third column. This is third row and first column, third row and second column, third row and third column. So according to this, 1 plus 1 is 2, which is even. So we will write a positive sign here. 1 plus 2 is odd, so we will write a negative sign here. Because in the formula for minor, we have to take minus 1 raised to power I plus j, right? So we are just doing that. 1 plus 3 is, here you would have positive, negative, positive, negative. Here it would be positive, negative and positive signs. According to, when you add these index, if they comes out to be even, we have to put a positive sign, otherwise a negative sign. Now what about the elements? In order to find the element, suppose for this particular element, you will see in your matrix, this is your, for this position, you will delete this row and delete this column and multiply the elements together. So you see 1 minus 0 is 1. So you here the entry comes out to be 1. In a similar fashion, you can calculate it for this element. You will delete this row and delete this column. So you see this is 0 in minus 0. So this element comes out to be 0. In a similar manner, you will calculate all the elements. Then whatever this forms the cofactor matrix of the matrix A. Then in order to calculate adjoint A, you take the transpose of this matrix, which is this matrix. So A inverse would be, because the determinant comes out to be 1, you have to divide each entry by 1. So it is just the adjoint matrix. So this is the inverse matrix. Hence this for each matrix of such kind, we have found an inverse element which is also present in the same set, right? Hence all the group axioms are satisfied, and we say this set forms a group under group operation multiplication. So I hope you understood this question well. That is it for this video. Thank you for watching.